transformations to lines and to planes and then to a curve, specifically a circle. And that is related to, well, that's kind of like a cute trick, but what we're really interested in is what happens, for the context of integration, what we're really interested in is what happens not just to curves or to surfaces, but what happens to regions when you transform them under linear transformations, because we're interested in what happens to little delta A's and what happens to little delta V's when you transform them under a linear or nonlinear transformation, which is what a coordinate change is. If you carry out a coordinate change, what you're doing is a transformation, and what happens to the little delta A's and delta V's. So let's talk about that. Where are my pretty notes? Okay. Linear transformations. Linear transformations. Continued again. Okay. Consider a linear map or linear transformation T going from R2 to R2, represented by a matrix A, which I'm giving coordinates A, B, C, D. This map will transform a square in R2. Okay, so what I'm going to do is I'm going to take the unit square. I'm going to take a unit square in R2 and I'm going to transform it under this ABCD transformation, see what it turns into, and then what I'm really interested in is the area. What's the area of the image? This map will transform a square in R2 with vertices at 0, 0, 1, 0, 1, 1, and 0, 1 into a parallelogram, and we've already seen that with that example with the dots, number 61, I think it was. With vertices. Okay, now think about it. If you take that matrix A, B, C, D and you multiply it by each of those points expressed as a column vector, you'll get 4 new points, and the points are 0, 0, 0. AC, I'm just checking if my notes follow the same order, but they do. A plus B, C plus D, and BD. Okay, all right. In other words, we've taken a square that looked like this, and we've turned it into a parallelogram. Now, of course, it completely depends on what those numbers A, B, C, D are, what your picture's going to end up being. Try and draw that as a parallelogram. Okay, something like that. The origin has stayed at the origin, but the other points have moved. Now, I've chosen to draw my parallelogram like this in the first quadrant, but if some of those A, B, C, D were negative, you actually might get it in a different quadrant. So I'll just write here. Or we could have got something like that, or we could have got something like that. It really depends on what. There's obviously many options depending on what your A, B, C, D are. Okay, but I'm going to look at this one over here. There's my height. I've dropped a little perpendicular there. What I'm interested in is the area of that image. I'm interested in the area of the parallelogram. Question?
Will it always give the parallelogram function?
Yes, it will. The reason for that, so the question is, will you always get a parallelogram? And you will, and the reason for that is that, and I haven't proven this, but I can prove it, linear transformations maintain the parallel property. So if two lines, remember if you take a line and you transform it under linear transformation, you get a new line. You don't really know ahead of time what line it's going to be, but you know it's going to be a line. If you have two lines that are parallel and you transform them both under the same transformation, they will still be parallel. Perpendicular orthogonality is not maintained. If two lines are orthogonal and you transform them, they don't necessarily end up orthogonal. But if they're parallel, they do. So because a square has that condition that the two pairs of opposite sides are parallel, you will end up with a quadrilateral that has two pairs of parallel sides. But because the angles could have gone all funny in the meantime, the best you can say is parallelogram. Question?
Could it transform a square into a point?
Yes, could transform a square into a point by just dropping the dimensions. Yeah, that is true. That is true. Or, in fact, a line. Am I correct? Well, a line segment. Where a point would be a sort of a twice collapsing of dimensions. A line segment would be a one collapsing of dimensions. That, of course, would be unusual. Generally, we're turning a square into a parallelogram. Okay, so what is the area of the parallelogram? Area of parallelogram. Well, the formula for the area of parallelogram is length times height. Base, the length of your base times your perpendicular height. Okay, the way I've drawn it, the length of my base is the modulus of the vector AC. And then my height, I would have to do a little sine calculation, a little trig calculation. So let me draw a theta in here. It's going to be the modulus of vector BD sine theta. And I'm going to put, is it really necessary? I always put modulus signs here because in our picture theta is acute. But even if it were obtuse, sine theta is still positive. But you know what? Seeing as I am defining theta here as being the angle between vector AC and vector BD, there are, depending on what, it could in fact even be a reflex angle. So I'm putting the modulus in there because this is an area, okay? There's an area in our picture. We don't need the modulus signs, but in a different picture we might, if theta were actually a reflex angle. Okay. And that modulus of a vector times sine of the angle between them. That's the cross product, and more precisely it's the magnitude of the cross product. I think some people said dot. Maybe I was mishearing. Dot product has a cos theta in it. Cross product has a sine theta in it. But whereas your dot product is a scalar, your cross product is not a scalar, so that expression with the sine theta in it is not the cross product, it's the magnitude of the cross product. Okay? And then you can actually work out that cross product, because we've got vector AC 0 cross with BD 0. So you can do a little crisscross dot product and work out the result, and you get that. That is the cross product. You can work it out the side of your page if you want. And the modulus of that vector is just AD minus BC, which is the modulus of the determinant of A. Now, my original square had unit area. If my original square had actually been slightly bigger, then my parallelogram would have been probably bigger. And it would have had a larger area. So more generally, area of image is the modulus of the determinant of A multiplied by area of original. In our case, the area of our original was just one square unit, so it didn't show up. Just looking at all the various people at the tutorial yesterday who assured me they'd be in today's lecture. Yes, you are. Thank you. Thank you. You may be the only one of that particular cohort. Yeah. Okay. And that is very, very powerful. That is incredibly powerful. Because it means that if you have two areas that you know are related by some sort of transformation, if you work out the one area, you're able to work out the other area by simply this relationship between them. Turns out to be very useful, and it's this property that we're going to be using when we do coordinate changes. When we do coordinate changes in integration, these area of image, area of those are going to be delta A's. Those are going to be delta A's and ultimately dA's in our multivariable integrations. Yeah?
What is the determinant of A?
Well, A is the matrix that represents the matrix, and the determinant of a 2 by 2 matrix is that what you're meaning? How do you work it out? Yeah. So the determinant of a 2 by 2 matrix is simply the product of the two numbers on the main diagonal, subtract the product of the two numbers on the other diagonal. So if that was a lapse of memory, that's fine, but just for my purposes, do you know how to work out determinants? Was that covered in first year? Okay, I'm hearing yeses and nos. Can I please have a show of hands? Who feels very confident that you were never taught determinants? Okay, all right. Okay, because I'm going to expect you to know how to work them out, and 3 by 3 as well. 2 by 2 is easy, but 3 by 3 gets a little messier, yeah? Well, I'm basically giving that to you without proof. But you can determine that for yourself. For instance, if you put those as 2, 2, you have a 2 there and a 2 there, and then you transform those points, you're going to get a picture very similar to that, but the vectors are going to be full of 2's. And those 2's are going to come out over here, and eventually they're actually going to come out as a 4, which is going to end up multiplying 2 2's. And what you're going to end up with is the same determinant multiplied by 4, where 4 is the area of the original. So I am giving them to you without proof, but you can determine it with a little bit of experimentation.
Can you just remind us what the determinant is actually like numerically used for and like what significance it has?
Yeah, so the determinant is a rather mysterious sort of number. What is the determinant? I'm not sure that I can give one single answer to what is the determinant. It's tempting to say that it's related to the... No, I don't even want to put myself on audio saying things that are on a video that are not entirely true. When you work out the determinant of a matrix and you end up with a number, that number by itself can be used in various contexts, but the number by itself is very hard to say that number is indicative of a certain quality of the matrix, except with one particular exception for when your determinant is 0. Because if your determinant is 0, then your matrix cannot be inverted. And you call your matrix a singular matrix, and those matrices are special animals. So when your determinant is 0, you can draw some immediate conclusions about your matrix. If your determinant is non-zero, you can use that number in various ways, like here, but it's almost an effect size of the matrix, a sort of a measure of how big an effect it's going to have on things when it acts on things. But even that is too fluffy.
We use it to find out different quantities of the matrix. We use it in calculations to do with matrices.
Yes, you use it in calculations to do with matrices and to do with the action of a matrix on something.
I'm pretty sure that mainstream in 21 didn't do the 3 by 3 determinant.
Okay.
We did the 2 by 2.
Okay. All right. Good. No, it's good to know. When we get to a 3 by 3 example, I'll slow down and I'll work through the process. So it's easy once you've done 1 or 2. It's very mechanical, but you just need to see it done. Okay. And this idea, and by idea, if you could please keep quiet, I mean that a linear transformations, when you transform a region, in this case a square, you can relate the area of the image to the area of the original by the determinant of the matrix. That's the idea I'm referring to. I'll get to you in a sec. This idea can be extended to 3 dimensions. Okay, but you had a hand up over there. Are you fine? Okay. Such a map transforms a unit cube into a parallelepiped. I can remember that the very first physics problem set, do you still get physics problem sets? The very first physics problem set that I ever got at university had the word parallelepiped in it, and I'm still scarred. It's a beautiful word, I love it, but there was no explanation given. We just had this physics problem and it referred to a parallelepiped. What? And there was no internet then. You couldn't just go to Google and put in parallelepiped. I didn't know what it was, I didn't know how to say it. There you go, parallelepiped. And what is it? It's basically a box. Think of a rectangular box, only instead of all the sides being rectangles, all the sides are parallelograms. Okay, so this gives me a marvelous opportunity to draw a parallelepiped, and one shouldn't turn up an opportunity like that. Okay, so imagine that these two down here form the base of my parallelepiped. There we go, these two vectors. Okay, there I've got my parallelogram base of my box. Okay, I'll try and draw a good picture here. Something like that. Yeah. There you go, there's a parallelepiped. Isn't it pretty? Okay, I'm going to call this vector A. I'm going to call this vector over here B, and this vector over here C, and the parallelepiped is basically formed out of those 3 non-parallel vectors. So what I'm going to do is I'm going to drop a perpendicular from the tip of C down to the base, and that's the height. Okay, and I'm going to say the volume of my parallelepiped is the area of the base times the height. Okay, cool. The area of the base, well, you know that the area of a parallelogram is the modulus of the cross product of the 2 vectors that created that parallelogram. Go scratching back in your vector geometry notes, that's there. Any 2 non-parallel vectors can be used to describe a parallelogram, and the area of that parallelogram is the modulus of the cross product of those 2 vectors. Isn't maths awesome? Maths is just so awesome. Yes, it is. It's absolutely awesome. I'm sorry I suggested going back home to bed, because then we would have missed this. When I came in here this morning, it was very dark. I suggested that we all just go home. I didn't suggest it seriously. That would just be ridiculous. Okay, all right. Okay, H. Let's have a look. I'm going to put theta over here, and I'm going to get my H with a mod C cos theta. In fact, modulus of cos theta, because we just want to make sure that everything's positive. In my picture, theta is acute, but in a slightly different picture, maybe theta wouldn't be acute. So let's just put the moduli there, modular signs. Okay, now I'm quite deliberately choosing to put my theta over there rather than my theta at the bottom, because I want to notice that I can actually draw A cross B into my picture. A cross B will be up here. Orthogonal to the base of my parallelogram, orthogonal to A and B. And by all that parallel line geometry that I learned back in high school, I know that that angle over there is theta. That's not a very nice looking theta. Let me try again. There you go. When do you do parallel line geometry? Grade 8? Grade 9? Alternate angles, corresponding angles, all that jazz. You still do that? Please tell me you still do that. Please tell, they kind of gutted the school syllabus so badly. This is sad nods. So yes, they have. Yeah?
Just put in maths paper 3 and then brought back with the CAS syllabus back to you.
Oh right. So you're the lost generation that didn't do parallel line geometry. Are you aware that those two angles are equal? And those two angles actually have a name. They're called alternate angles. There's a bunch of you who are saying we totally did that, guys. We did. Stop pulling the wool over the lecturer's eyes. Anyway, let's not digress too much about the school system, where a lot of people are trying very, very hard to make it all work. Okay. Okay, and when you have modulus of a vector times modulus of a vector times cos of the angle between them, please keep quiet, because notice theta is the angle between C and A cross B, then that simply is the dot product. More strictly speaking, it's the modulus of the dot product. Because of that cos, there are modulus signs around the cos theta, and that's what's insisting that we have modulus signs here now. And that thing that's inside those modulus signs has a special name. What's it called? Okay, yes, it is to do with determinants, but I'm actually looking for something else. It's the something product. The scalar triple product. Somebody say I told you. It reminds me of a time when my younger daughter was in, I think she was in, no, she wasn't. It was my older daughter was in grade R, so my little one must have been about 4 years old, 4 years old. And we were walking through a parking lot, and there was a car that had just stopped, and its engine was still warm. You could feel the warmth coming off the car. And so she said something about, why is it hot? And I said something, I wasn't in a very good mood in the morning. We'd probably had a bad morning getting dressed and eating breakfast and stuff. And I said something about, because the process that takes place in the engine is an exothermic reaction. And she said, I knew that. At age 3. She didn't actually know that. That's just 3-year-olds for you. So there you go. So you knew it was scalar triple product, whoever said that out there. She's still just as difficult today. Yeah. Okay, so more generally, so what's happened here? So what has happened here? That in fact is it is the determinant of A, as was mentioned in the middle there. So what's happened here is we have a unit cube, and we've transformed it into a parallelepiped, and the volume of that parallelepiped is now, in order to prove to you that this funny looking cross dot thing actually is the determinant of A, I can do it very easily, and it would fill an entire screen with little A's and B's, A, B, C, D, E, F, G, H, I's, because I'd need 9 little letters. And it would be a huge mess. So I could show you, it would be very easy to show you, but it would be a huge mess, and copying it down wouldn't be fun. But what you could do, so let me explain. You could have your vector A and call it, you can give it the components A1, A2, A3, or whatever you wanted to. And B, maybe call it B1, B2, B3, and C, maybe call them C1, C2, C3, or maybe call the components A, B, C, D, or whatever you want to call them. Give those vectors components, and actually carry out the cross product and carry out the dot product using those little components. And you'll end up with a long string of terms where each term is going to be the product of various little letters. Meantime, if you use those components as your columns in your matrix, so A1, A2, A3 is the first column, B1, B2, B3 is the third column, etc. Do I want columns? Do I want rows? I think I want columns. And you work out the determinant of that 3x3 matrix using a process I will demonstrate at some point. You will get that same string of terms where each term is the product of little letters. Demonstrating it to you, I think, would be a complete waste of time because it would be very boring. It would be a sea of little letters and numbers. But you can do it. It's not hard. It's multiplication. It's what it all boils down to is multiplication. And we can all multiply. What's the time? 32. I'm getting too digressed in talking about random stuff. But even in the 3D case, in general, the area of the image is the modulus of the determinant of A times by the area of the original. And of course, that becomes pertinent when we do dVs, delta Vs. Okay, all right. I don't think there's anything else I want to say about. Let me actually just write down something that I've said verbally but haven't actually written down. Interesting side note. Linear transformations. Maintain is not the right word. They I'm going to say maintain. I don't think it's the best word. Maintain the parallel property. The parallel property. Parallelness, basically. So you can write parallelness if you want, but I don't think it's a word you'll find in the dictionary. Two parallel lines transform to two parallel lines. Linear transformations do not maintain angles and hence do not maintain orthogonality. Okay, all right, that was just a little thing. Again, that can be proven. I'm not going to. I am going to finish off the linear transformation section with doing exercise 78. Okay, which is a little bit of a jump again. Now, basically what we're doing here is we're coming back to the definition of linearity. Remember when I gave you that introductory paragraph, etc., for linear transformations, I said here is a thing that we'll come back to when we do exercises 78 and 79. That's now. Which said that if you have a linear transformation and you want the matrix that represents it, the columns of the matrix that represent it are the vectors that you get when you apply your transformation to the columns of your identity matrix. A question over there?
Would you mind just going up and just explaining what A and T are? Because T, like, just
T. So T, capital A and capital T. So capital A is a matrix. We'd use T if we were writing it in, I'll go right to the very top, if we were writing it in sort of a function form. Okay, so that T of R2 to R2, if we had an actual example, would look something like T of x, y equals 2x plus y, 3x, that sort of thing. And so that's function notation. And so that capital T is basically playing the same role as little f when we do functions. With linear transformations, it turns out that we don't have to write it in function form. We can write it in matrix multiplication form, and then we don't use that letter T because that's the function name. We use a different letter for the matrix it represents it, and that's capital A. So capital A and capital T are really just, they represent different modes of expression. One's a sort of matrix mode and one's a function mode, but they're describing the same process.
So we're taking the determinant of the map, not the determinant of the...
You're taking the determinant of the matrix that represents the map. Yeah. Okay. So just because of this whiplash change of topic here, remember the definition of linearity. T of alpha x equals alpha t of x, and t of x plus y equals t of x t of y. My good friend Trevor Clutie, who teaches dynamics, will use that to represent, well, in fact, he very rarely uses x and y. He'll use something like, in the example that we were looking at the other day, I think it was b. He'll use b with the arrow on top to represent the actual vector, and he'll use b without the arrow to refer to the magnitude of the vector. He thinks this is a very logical notation, and it is a logical notation if you don't keep in mind that students, and I'm throwing you all here into the same basket, drop their arrows all the time. So don't drop your arrows, particularly when in the presence of people who don't seem to be aware of the fact that dropping arrows is a thing. So don't drop your arrows. They're important. They mean a thing. Also recall the columns of A are T applied to the columns of the identity matrix. Okay, you can see that very easily in a typical example. Let's say T of xy is 2x plus y 3x. Okay, we would say that the matrix that represents it is 2, 1, 3, 0. Please keep quiet. Just think about what T of... Okay, now that's 2 by 2. 2 by 2 matrix only has 2 columns to its identity matrix, 1, 0, and 0, 1. T of 1, 0 is 2, 3. And T of 0, 1 is 0, 0, 1, 0, 1. Ah, yes. So I'm confusing myself. X is 0 and y is 1. Yes, yeah, okay. Yeah. So there's a simple little linear transformation written in function form. If you apply that function to the 2 points 1, 0, and 0, 1, or the two vectors, I should say, 1, 0, and 0, 1, you'll get out the vectors 2, 3, and 1, 0, and those are the columns of your matrix it represents. It's very obvious, right? Why do you even need to know this fact? Because, look at it, it's so obvious. It comes in useful in examples like 78.
Sorry.
Yes.
About one example.
Yeah, talk to me, yeah?
About one example is that.
Oh, I just totally made that up. This is just me demonstrating that, so when I say the columns of A are T applied to the columns of the identity matrix, which are often called the elementary vectors, I'm giving that little made-up example to you to justify that my statement is a true statement. So here we have T applied to 3 vectors, and that's all we know about the transformation. Okay, that's all we know. We've only been given those 3 facts, and we now need to figure out what is our transformation, particularly what is the matrix that represents it. Okay, so A is going to be equal to a 3 by 3 matrix is going to have to be 3 by 3 because my input is 3-dimensional and my output is 3-dimensional. And the first column is going to be t applied to 1, 0, 0. And the second column is going to be t applied to 0, 1, 0. And the third column, I drew my bracket too close, is going to be t applied to 0, 0, 1. And if I can find those three vectors, I'll have the columns of A. Well, the middle one's easy, because it's been given to me. But the other two have not been given to me. So how am I going to find them? I'm going to find them like so. I want to know what is t's action on the vector 1, 0, 0. So what I'm first going to do is I'm going to construct the vector 1, 0, 0 out of those three vectors that I do know t's action on. 1, 1, 1 minus 0, 1, 1. Do you agree that the statement that I have just written is a true statement? I've very, very carefully chosen that. Those two vectors on the right appear in my little set of three information points. Okay? Beg your pardon? Then you just have to come up with a more complicated linear combination, like maybe 2 of these minus 1 of those plus 3 of those, yeah, which would be a bit of a pain. But this you can at least do by inspection. Now, linear transformations say it doesn't matter if you carry out the sum first or you carry out the sum second. If t were a nonlinear transformation, you could not say that. Because on the right-hand side, I have two vectors. I'm carrying out the transformation first, and then I'm subtracting. On the left-hand side, I effectively have the two vectors already subtracted, and I'm carrying out the transformation last. Yes?
The thing that's only true if it's linear is that the fact that difference is true, or just the fact that you can do the transformation first or after?
The thing that you said second. that it doesn't matter whether you carry out the transformation first before the subtraction or whether you carry out the subtraction first and then the transformation. That's the thing that's only true if. So that statement over there with one vector equaling the difference of two vectors, that of course is always true. But saying that it therefore follows that the t of the one thing is the t multiplier, etc., that only follows if t is linear. Yes?
I'm sort of lost. Why aren't they taking the t in terms of x and to a certain vector?
I want to know what t of 1, 0, 0 is. Because if I know what it is, it'll give me the first column of A. And I don't know what it is. But I can figure out what it is from the information I've been given. Because I know how the vector 1, 0, 0 relates to the vectors I have been given. And so by the definition of linearity, I can work out what t of 1, 0, 0 is. Which is going to give me the first column of my my representative matrix. Okay, we are running out of time, so I also need to know 0, 0, 1. So I'm going to build 0, 0, 1 out of the vectors that I've been given. There you go. It follows, due to linearity, that t of the thing on... Look, here's another way of saying things. Whenever you have an equation, you can always do things to both sides as long as you do the same thing to both sides. So t of the left will equal t of the right. Okay? But only if t is linear can you split it. I mean, just think about log laws. Just think about logs. If I have a equals b plus c, I can say log of a is equal to log of b plus c. But I can't say it's equal to log of b plus log of c. So you can always do something on the left and right as long as it's the same thing and you do it to the entire thing. Splitting it up, that's often not true. And if t were not linear, then I wouldn't be able to do this sort of split thing. But because t is linear, I can. So there's a slightly different way of looking at it. We are basically at the end of the period, so if you have other questions, I'm happy to answer them, but I need to get the notes done. And that's 3, 4, 5. Subtract, I've scrolled past it. Minus 1, 2, 1. 3 plus 1, 4 minus 2, 5 minus 1. So I'm rushing a little, so I hope I'm not making mistakes. Sorry, people who are copying down, I just need to write out what A is. And now I've scrolled past all my useful information. That one's a minus 5, that's a minus 3, that's a minus 4. The last one is 4, 2, 4. And what's the one I'm missing? So I've scrolled past it. Minus 1, 2, 1. Okay, that one in the middle was given to me. The other two I needed to work out. Okay. Okay. Let me pause there.